All right. Today we're talking about the normal distribution. If you read this little blurb here, they kind of talk about how we as a species are getting taller as the decades and centuries go by. Well, if we continue reading, it says below are histograms constructed from data collected from adult men in reference to their heights. Note the sample size is increasing from left to right. So if you look at a random sample of 100 men, it looks kind of like the histograms you've been creating. As we up it to 500 men, the class size gets smaller and smaller. As we go to 1,000 men, you can see it kind of gets smoother as it goes up. And if we applied it to the entire population, it'd actually be a smooth curve that's going to follow this shape here at the end. Well, that shape right there is known as a normal distribution. So as sample size increases, the histogram would approach what's called the normal distribution. And if it's not quite, we force it to be in that normal distribution so we can talk about it as an entire population. Remember, when we're talking about inferential statistics, we're talking about applying it to an entire population. So the normal distribution is a way for us to apply data to an entire population so we can talk about it as a whole. So as we continue on, well, a normal distribution is what's called a bell curve that shows how data is distributed from the mean. So it's showing distribution around the mean. Now, I do want to put something on here. If you notice your bell curve, it's kind of a mirror image on both sides. So if I would draw a line right down the middle of it, we'd see that both sides are mirror image of each other. Now, about 2 days ago, we learned that was called symmetric. And why that's important is, well, remember with symmetric graphs, your mean was about the same as the median. So your mean and median are going to be the same. So when we're talking about the mean, we're actually saying, well, the median's the same, so we're just going to primarily talk about the mean. We won't talk about the median when we're doing normal distribution, and that's because your median and mean are the same. If we look down below on this blurb here, we kind of talk about why the normal distribution is so big for statistics, and that's because there are tons of phenomena that resemble this type of distribution. Examples included heights, weights, intelligence quotients, that's your IQ scores, SAT scores, prices paid for a new model of car, and even lifespans of light bulbs follow a normal distribution. In fact, if you think about things like soda, when you buy a soda and it says it's 12 ounces on there, there really aren't 12 ounces on there. In fact, the Coca-Cola company spends a ton of money on statisticians to study how much soda is going in there to create an actual bell curve so that there is at very least 12 ounces in there. So most of the time when you get a can, there's actually more than 12 ounces in there because machines, as awesome as they are, can't get to the precise ounce a million billion times over. Another way you might have heard about normalized curve is if you ever heard of a teacher saying they're curving the test. This is actually what they're doing. They're trying to normalize the test where if we look at that bell curve, they're going to try to put maybe like a B, a high B, right at that mean. And then as it distributes around, we have A's going to the right and lower grades going to the left. So depending on what grade they're looking for, they'll normalize that curve and put whatever grade they want smack dab in the middle. And that is why it's called curving a test. They're putting it against a bell curve or a normal distribution. When we're talking about normal distributions, you're going to hear deviation, standard deviation, over and over and over because it plays a huge role when we're talking about normal distributions. So the standard deviation, which we just calculated, plays a crucial role in normal distribution as summarized below. So if we look below at this little graph here, if you look at that 0, 1, 2, 3, negative 1, negative 2, negative 3, those are actually talking about your standard deviations, where that 0 is going to be your mean. 1 would be one standard deviation. So 2 would be two standard deviations. Now remember, your standard deviation isn't usually 1. So usually your mean might be 87. So if you look at that 0 and maybe in what you're studying, your mean is actually 87, that 0 replaced with an 87. If your standard deviation was 6, that 1 would replace with 87 plus 6. So you talk about 93, then you add 6 again to get to the 2, then you add 6 again to get to the 3. So really it says 1 standard deviation, but what we're actually doing is we are going 1 times whatever our standard deviation was, and then we add it to the mean. So 2 would be 2 times our standard deviation, and add that to the mean. Now, when we break that apart, if we look at these, it's called the 68, 95, 99.7 rule. Approximately 68% of data fall within 1 standard deviation of the mean in both directions. So if you look at that 1 and negative 1, between those, 68% of your entire data lies right there, which means we can actually subdivide that even further. We can say, well, between 0 and positive 1 would be 34%. And between 0 and negative 1, 34% of our data is there. Now, if we continue reading, it says approximately 95% of the data falls within 2 standard deviations of the mean in both directions. All right, well, if we keep subdividing further, well, we excuse me, between 0 and 1, we have 34% of our data. Between 1 and 2, we are going to have 13.5% of our data, which means between negative 1 and negative 2, we'll also have 13.5% of our data. In other words, 13.5 plus 34 plus 34 plus 13.5 would give us 95%. Now, going further out, 99.7% of our data falls within 3 standard deviations of the mean in both directions. Well, adding on to that, that would give us 2% of our data is between 2 and 3. 2% of our data is between negative 3 and negative 2. And finally, 0.5% of our data is left over on what's called the tails. So anything past 3 standard deviations is known as a tail. Those are really high or really low values. They're very, very rare. Most of our stuff is going to happen between 3 and negative 3 standard deviations because 99.7% of our data is in there. If you look at kind of this curve, this is where they come up with percentiles. Like when you take a big test and they say you're in the 90th percentile. They're actually looking at your standardized curve. Where do you fall compared to everyone else? So that is one place where you probably have heard of a curve also. All right, continuing on. We're going to do an example. It makes a little more sense if we do an example. So it says the grades on a math midterm are normally distributed with a mean of 81 and a standard deviation of 5. We are supposed to draw and label the normal distribution of a curve. So what we're going to do is we're going to start off by drawing a straight line. And maybe I should move that up a little bit higher. Let's put it about there. All right, then we're going to draw basically that curve that we have on the other side of the sheet. All right, it looks something like that, or perhaps you can draw it better. Note my tails here. They don't actually touch. They will never touch. I know on the other sheet it looks like it's touching, but when we draw it by hand, we show that they don't touch because we're saying that basically it can be any value out there. We don't know where it ends. So those aren't actually going to touch. All right, now what we're going to do is we're going to draw some lines. We're going to draw one line that goes smack dab through the middle. This is going to be our mean. Then we're going to draw 2 lines that are basically the same width away from our line, maybe something like that. That's going to be 1 standard deviation. Then we'll put 1 more line on either side. And then we need 1 more right there, right there. If you look at the other side of the sheet, some people do drag these up. So some people will actually draw lines like that. I usually just draw them inside of the curve. All right, now let's put our data that we were given. It says that the mean is 81%. Well, remember, this central line is going to be our mean. So when we put our mean, we're going to put 85. When we go to the right, that is 1 standard deviation more. So it's plus 1 standard deviation. Well, it says our deviation is 5. So we're going to do scratch that. Hang on. Our mean was actually 81. Let me get that fixed. All right, our mean was actually 81. So when I add one standard deviation to it, I'm going to add 5 to it. So that's going to become 86. All right, our next line to the right would be 2 standard deviations, which would be 86 plus 5. So then we would have 91. Then we'd add one more to that and make it 96. Would be our last one we're going to list. All right, then we'll continue on, and we'll go, okay, 81 minus 1 standard deviation. So this one's minus a standard deviation. So 81 minus 5 would be 76. Subtract 5 again, and we'd have 71. Subtract 5 again, and we would have 66. All right, note that the rules that we had here will now apply to this graph. I.e., if I was looking at the distance between 76 and 86, that would be our 68% of our data. So this would be 68%. Then if I did my next two, that would be between 71 and 81. We would have that, so if we look at the next line, we have 95%. And finally, our last one, which I drew a little bit high here, that would be our 99.7%. Now what I always do before I start doing my work is I actually subdivide it kind of like I did on the other side. I said, well, 68% divided by 2 would be a 34% and a 34%. Then going further out, we'd have that 13.5%, that 13.5%. Continue on, we'd have that 2%, that 2% here. And finally, our tails are smalls, which are 0.5% and a 0.5%. That's just going to make answering these questions a little easier because then we don't have to break it down later. All right, so let's look at those questions now. All right, A said draw it. B says what percent of data falls between 76 and 86? So if we look at 76 and 86, we're looking at all of this data here. Well, that's 34 plus 34. In other words, it's that 68%. 68% of our data falls between one standard deviation on either side. Well, that is one line, another line, so that's 68%. Then it says what percent of data falls between 71 and 91? Well, 71 and 91 are 2 standard deviations away from the mean in 2 directions. That's going to be our 95%. Next it says what percent of data falls between 81 and 91? Well, 81 and 91 would be that 34%. So let's highlight that really quick. So we're talking about this plus this. This is why I break it down. It makes it a little easier now. We're going to do that 34% plus that 13.5%, which is going to give me that 47.5%. Finally, it says what percent of the data is less than 86? Less than 86 would be this 34%, this 34%, this 13.5%, this 2%, and this 0.5%. So that is going to give me what? 84, let's change that back to black, 84%. Because it's 34 plus 13.5 plus 2 plus 5. Alternatively, you could have done 100% minus 13.5 minus 2 minus 0.5. You would have got the exact same answer, whichever method you prefer. All right, the last thing we're going to talk about is something called a z-score. A z-score is going to be a score so we know how many standard deviations something is away from 0. Rather than knowing that I'm at 86, we're going to know it's 1 standard deviation. So when we're talking about z-scores, it shows how many standard deviations a value lies from a mean. Now the formula for this is data item. So the value that we have minus the mean all over our standard deviation. Which another way to do it with symbols would be x minus x bar, remember x bar is our mean, over our sigma, which stands for our standard deviation. All right, let's do an example with this. So it says the mean weight of a newborn infant is 7 pounds, and the standard deviation is 0.8 pounds. The weights of the newborn are normally distributed. Find the z-score for the weight of the following. All right, let's go ahead and first let's label this curve. Normally you wouldn't have to do this with z-scores because that's the point of z-scores, is so you don't have to draw this, but let's just practice it. So in essence we draw 3 lines to either side. That central line is our mean. It said our mean was 7 pounds. And then our standard deviation is 0.8. So we're going to add 0.8 to both sides. So we'll have 7.8. We would then have 8.6. We would then have 9.4. We would have 6.2 on the other side. Then we'd have 6.2 minus 8, which would be 5.4. And finally, we would have 4.6. Once again, the whole point of z-scores is so I don't have to draw this, but I want you to see what the z-score does and where it would be on the curve if you're just picturing it. All right, it says calculate the z-score for a 9-pound baby. So our z-score, remember, is x minus x bar all over our standard deviation. Well, in this case, our x is 9, our median was our 7, and our standard deviation was 0.8. So if I would do 9 minus 7 divided by 0.8, I'm going to end up with 2.5. So what that 2.5 means is you are 2.5 standard deviations away from the mean. So that is 2.5 standard deviations from the mean. And if we think about standard deviations and how it works with the curve, well, 2.5 standard deviations is past this number. In fact, it's right here. Well, that's pretty far out. And if we look at the graph that we have here, well, 9 pounds, 2.5 standard deviations. If we list our standard deviations down here, we'd have 0 standard deviations, 1, 2, 3. 2.5 standard deviations is right here. That's where our z-score of 2.5 is. Well, that's a pretty large baby. Look at all the percent. I mean, all of this is less than that size of baby. So we have a pretty large baby. When we start talking about 2 standard deviations, you are going away from the mean pretty far. So 2.5 on a z-score is pretty far away from the mean. Our next one is a 7-pound baby. Well, if we're calculating the z-score of a 7-pound baby, that would be 7 minus 7 divided by 0.8. Well, that equals 0. Well, that makes sense because our mean was 7, and so our z-score is going to be 0. Our z-score is 0 here because it's 0 deviations away from the mean. It is the mean. 7 pounds is the mean. So that would be an average-sized baby, where 9 would be pretty big, 7 would be average, 6, let's check out 6. So 6, our z-score would be 6 minus the mean divided by 0.8. If I did 6 minus 7, divide that by 0.8, I'm going to end up with negative 1.25 standard deviations. So we're just going in the negative direction. So this would be under 6.1. That would be a z-score of negative 1, a z-score of negative 2, a z-score of negative 3. Remember, these are just standard deviations. So it's negative 1 standard deviations from the mean. We are at negative, what was that? Negative 1.25, which would be maybe about here, would be our negative 1.25. Well, it's a little small. We're still within that. We're still within that. 90. What would that one be? That would still be within that 95% of our graph. Yeah, because we're not quite within our 70 or 68. Our 68 would be here. We would be within our 95%. So that would be within our 95%, a little bit bigger than our 96%, but 1 standard deviation isn't too bad. It's when we start getting to that 2. So relaying this, the bigger the z-score, the farther you are from the median and the mean. So when we had 9 pounds, 2.5, that's a really big baby compared to other babies. A 7 pound, that was exactly average because it's 0. 0 is mean. Negative 1.25, although more than one standard deviation, still isn't too far the realm, because we're looking for that 2 standard deviations to be really that extreme value. All right, so that's how z-scores work. They just work with our standard deviation. They are how many standard deviations they are away from the mean. All right, but that basically covers our normal distribution. Hopefully everything made sense and you don't have too many questions. Hopefully you watched this video too. I'll see you guys on Monday.